Our title for this project is Frequency Response of a Robotic Position Control System, which consists of 4 group members, which are Koay Wei Loon, Khor Weng Jie, Ewe Jo Min, and Yip Jun Hui. My name is Khor Weng Jie. I will talk basically on introduction part. A standard robotic position control system usually has 6 degrees of freedom. 6 degrees of freedom is a specific parameter count for the numbers of degrees of freedom an object has in 3-dimensional space, such as the real world. 6 degrees of freedom consists of the following movement parameters, which are translation and rotation. For the translation, which is moving along the different x-axis, x, y, and z. For heaving, which is moving up and down along the y-axis, while for surging, which is moving forward and backwards along the x-axis, while for swaying, which is moving left and right along the z-axis. Next, for the rotation, which is turning in order to face a different axis. For pitch, which is moving between x and y, and for the yaw, is moving between x and z, while for the roll, which is moving between y and z. Next, a lead lag compensator is a component in a control system that improves an undesirable frequency response in a feedback and control system. In the circuit below shows that the right side, which is the lead part, and for the left side, which is the lag part. In this project, we are going to design either a lead or lag compensator to compensate the robotic position control system so that the phase margin will be at least 35 degrees. That's all for my introduction part. I will pass to the next part to my members.
Hi, my name is Koay Wei Loon, and today I will talk about the Bob plot calculation for the project. First, this is our transfer function. So the first step is we need to convert the transfer function above to the frequency transfer function, which means we need to replace the S with the J omega. So the frequency transfer is shown in here. So in the equation or in the function, 10 is representing the constant term, and 1 plus j omega over 5, 1 plus j omega, 1 plus j omega over 15, and 1 plus j omega over 75. Actually, they are 4 poles not at origin. To calculate the Bob plot, we need the first part is for magnitude plot. First, the j omega is equals to 10 over 1 plus j omega over 5, 1 plus j omega, and 1 plus j omega over 15, and 1 plus j omega over 75, where the k is equals to 10. So to proceed to the next step, 20 log j omega is equals to 20 log 10 minus 20 log 1 plus j omega over 5 minus 20 log 1 plus j omega minus 20 log 1 plus j omega over 15 minus 20 log 1 plus j omega over 75. This is the equation to plot the Bob plot for the magnitude. Second, for the phase plot section, angle for g j omega is equals to angle 10 minus angle 1 plus j omega over 5 minus angle 1 plus j omega minus angle 1 plus j omega over 15 minus 1 plus j omega over 75. For the angular 10, actually it is a constant term, so it has 0 phase angle and it has no impact on the phase plot. So the final equation for the phase plot is shown in here. For the coding for the bubble plot by using the Scilab, this is the coding to determine the gain crossover frequency with the phase margin. Another one will be phase crossover frequency with the gain margin. From the result, we can conclude that the gain crossover frequency is equals to 0.9402967 Hz and 1.3783222 Hz is for the phase crossover frequency. And the last part is phase margin is equals to 23.846 degree, while the gain margin is equals to 6.1356465 decibel. So this is the graph or the bubble plot that generated by the Scilab. In the graph, this is the gain crossover, which touch the line or intersect the line at 0. So from that, we can determine that there is a phase margin. So in this graph, the phase margin is positive. And during the line, in this blue line, this is the gain crossover frequency. By intercepting with the phase plot and the minus 180 degree axis, there is a frequency crossover. So this frequency is called by phase crossover frequency. From that, there's a gain margin can be determined in the graph, and the gain margin is positive. So I will pass another part to my friend. Thank you.
Hi everyone, my name is Ewe Jo Min and I will be talking about the phase lead system design. From the results we have gotten earlier, which is this one, we have known that the phase margin is equal to 23.846003 degree, while the gain crossover frequency is equal to 0.9402967 Hz. Since it's the answer we have gotten from the Scilab, the crossover frequency is in terms of frequency, and what we need for it is to be in terms of omega, so we have to times the answer with 2 pi, and after that we have gotten the answer of 5.9080581 radian per second. After this, we have to solve for the phi max, the alpha, and the tau. To find the phi max, which is also the phase margin we need, we have to use the phase margin required. From the question, the phase margin required is 35 degree, and we need to use it to minus with the current phase margin, which is what we have gotten earlier, this one, which is 23.846003 degree. And for this system, we implement a safety margin for it, and we assume it to be 15 degree. Then the phi max after calculating this all is equal to 26.15397 degree. And this phi max is equal to the equation of this sine power of -1, alpha minus 1 over alpha plus 1. So we times these both the left and right side with sine. So we have gotten the alpha minus 1 over alpha plus 1 is equal to 0.4408. Solving for the alpha here, we can find that the alpha is equal to 2.5765. To find the tau, we have to substitute the alpha we have gotten earlier, which is 2.5765 into omega m. This omega m is also given with formula 1 over tau square root of alpha. And after solving for the tau here, we will get the answer of 0.1054. And the final part of this is we have to substitute this alpha and this tau into the equation. This equation is a transfer function of the phase lead network. After substituting the answer here, we will get that the transfer of the phase lead network is equal to 1 plus 0.2716 J omega over 1 plus 0.1504 J omega. The overall equation, which is the compensator system after we have integrated the compensator with the overall system, is equal to 10 plus 2.716 J omega over 1 plus J omega over 5 times with 1 plus J omega times 1 plus J omega over 15 times 1 plus J omega over 75 times 1 plus 0.1504 J omega. Or we can also leave the answer in this form. By using the data here, we insert the data here into this Scilab so that we can get a more detailed, more accurate answer. And from the result, we can see that the new gain crossover frequency, which is the GCF here, is equal to 1.317901. Same with earlier, this answer is also in frequency, and we need this to be in omega form. So we have to times it with 2 pi, and the answer will be 8.28065389 radian per second. Through the Scilab, we also gotten the result of the new phase margin, which is the 27.723917, and this phase margin doesn't fulfill the requirement of the compensator, since the question needs ask for that the phase margin needed is 35 degree, and what we have gotten here is only 27.723917 degree. It's about 7 to 8 degree lesser. So we can conclude that the design for this phase lead network doesn't fulfill the condition of the compensator. Thank you. That will be all from me. I will leave the next part for another teammate of mine, which he will talk about the design for the phase lag network.
Greetings, my name is Yip Jun Hui. I will explain on the designing phase lag network. From the previous design, we found that the phase lead network does not fulfill the condition of compensator. So we're going to design a phase lag network. First, we need to calculate the new phase value. You can see here, this is the way we calculate the new phase value, which is we take a negative 180 degrees plus with the phase margin required, which is 35 degrees, and the safety margin, which is 5 degrees, and we got a negative 140 degrees. So from the graph, this is the gain crossover frequency, the blue line, and here is the negative 140 degrees here, and we got a 0.7212 Hertz. So the gain is 3.67 dB when the omega is 0.7121 Hertz. So to get omega, we have to times the 2 pi to become 4.5314332244 radian per second, and we will substitute the omega to find omega z. The omega z equals to omega c divided by k, where the k is the constant, which is 10. After substitute the value into the equation, you will get a 0.4531433244 radian per second. So next we will have to find the value of alpha and tau. To find tau, we will need this equation, omega z equals to 1 over tau. So substitute the value of omega z, you will get a 2.206807.308. To find alpha, we have to substitute the value of the omega c equals to 20 log alpha, and your alpha you will get a 1.525808395. So this is the transfer function of phase lag network. GC j omega equals to 1 plus j omega tau over 1 plus j omega alpha tau. You substitute the value of alpha and the tau into the equation, you will get 1 plus 2.206807.308 j omega over 1 plus 3.367165117 j omega. So this is the compensated system, the way to calculate the compensated system, which GC j omega times G j omega. All this, after calculate, this is the final answer, but you can leave it in this form So here is the coding of the phase lag network by using Scilab. So we will insert the value that we calculated to the Scilab. So it will draw a graph and it will show us this value, gain crossover frequency, which is 0.7225488, and phase margin, new phase margin 37.922998. So from the result, we get these two new phase margin and the new gain crossover frequency, but because that is that's only frequency, so to gain the omega we have to times 2 pi, so we will get a 4.539908004 radian per second. So with the phase lag network, the phase margin needed is 35 degree, but the result we obtain is 37.922998 degrees, which means is suitable to apply to the system. So in conclusion, the design for the phase lag network fulfills the condition of compensator. That's all from me, and thank you for watching.